So when you're talking about an optimization problem, what you're talking about is a problem where you have some particular quantity you're trying to optimize. Either you're trying to make it as large as possible or you're trying to make it as small as possible. But there's more than just that one element. You have what are called constraints on the equation. So constraints would be limitations on either that variable or some other variable that is used to compute the one that you're trying to optimize. So we have what are known as constraint equations, and we have the optimization equation. So for example, you might be looking for maximum airflow for a particular design of the hood of a car, or you might be trying to find the minimum amount of aluminum that can be used to manufacture a tin of food in order to hold a certain volume of food. You know, you want to hold 14 ounces. What's the minimum amount of aluminum you can use in a right circular cylinder shape? So in this section, we're going to talk about how to set up and solve those. So the basic idea of the objective function is the one that you're trying to maximize or minimize. So this is your optimization equation. The objective function is the optimization equation. Now, the constraint are limitations on some of the other variables that you have involved. So let's think about what some constraints might be. If you're talking about a box, the length, the width, and the height can't be zero. If there's zero, it's a flat box, which means it's not really a box in the true sense of the word. So length, width, and height have to be strictly positive. They also can't be negative. So that's a constraint on length, width, and height of a box. If you're talking about a right circular cylinder, something, you know, of this basic shape where it's got a circular bottom and it's a cylindrical shape, then we're talking about the radius and the height having to be strictly positive and non-negative. Now, there could be other constraints as well that are given in the problem. So when we're looking at these particular problems, we're going to talk about what the problem-solving strategy is, which is, of course, these are all word problems. So it's similar to the related rates problems that we did earlier this semester, in that everything's a word problem and you have to translate from the words into the mathematics. So the first thing you're going to want to do is define all the variables. So you're going to read the problem first, one time through, and just to get a vague idea of what you're talking about. Then you're going to go back, just like in related rates, you're going to break it down into the parts of speech, about every 2 to 3 words. And you're going to draw a figure and label all the variables. It's very important to make sure that you have all your variables defined. The next thing you're going to do, based on the words in the problem, is you're going to determine which one is trying to be optimized. Now, optimized is a generic word, meaning it could be either minimized or maximized. So this will be the objective function. So you might want to circle or highlight the variable that you're trying to optimize. So if you're talking about a box, you could have volume, length, width, and height, but it could be that you're trying to minimize the height as opposed to maximize the volume or minimize the volume. So it's not always the same variable, even when it's the same shape. The next thing you're going to do is determine the constraints on any of the variables. That is, what range of values for that variable are allowed. Now, some of the constraints will come from the words of the problem. So they'll actually be contained in the words, and you should have written them down as you were going through and translating in step 1. Some of the constraints are carried as a result of the situation. So they're not mentioned in the words. You have to know to write them down. For example, time can't be negative. Length, width, and height must be strictly positive. These are constraints that they probably won't mention, but they are a part of the problem. The next thing you're going to do in step 4 is you're going to write a formula. You've highlighted In step 2, the quantity that needs to be optimized. And in step 4, you're going to write a formula for that quantity in terms of the other variables that you found in step 1. So you've got all the variables written down and defined on your picture and in the notes that you took when you were translating. And then you're going to write a formula that relates those variables to the one that needs to be optimized. Then you're going to be taking the equations relating the independent variables in the formula from step 4, and you're going to look at the constraints, and you're going to use the constraints to replace some of the variables until you get a function of one variable, well, 2 variables, the one you're trying to optimize and one other. All right. So you're trying to rewrite the equation in terms of just 2 variables or one independent variable. The next thing you're going to do is identify the domain of consideration, the allowed interval for the function that you have in the previous step. That's part of determining the constraints of the problem. And then you're going to locate the maximum or minimum value of the function from step 5. Now, how do you find a maximum or a minimum? Well, there are a couple of ways. We can take the first derivative, determine where it's increasing and decreasing, and use that to find the relative extrema. So find the critical points, find increasing, decreasing, note the relative extrema. We can also find the critical points, take the second derivative and plug the critical points into the second derivative. If you get a positive, it's concave up, so it's got to be a minimum. If it's negative, it's concave down, so it's got to be a maximum. And if it's 0, you have to go back and do the increasing, decreasing. Okay. So now we're going to start with the examples. Most of what we're going to do today is just work examples. So we're looking now here at example 1. And there's a picture of a garden over here on the left. It's got a stone wall at the bottom of the garden. So it says a rectangular garden is to be constructed using a rock wall as one side of the garden and wire fencing for the other 3 sides. Given 200 feet of wire fencing, determine the dimensions that would create a garden of maximum area. What is the maximum area? So the first thing you have to realize is you've got some kind of rectangular garden space and you've got maximum area. So we know we're looking at a rectangle and we know we're looking for maximum area. So the first thing we're going to have to do is we're going to have to start going back and translating word by word. So that's our first step. Translating from one form of writing English into another form of writing mathematics. Okay, so going back to the beginning, a rectangular garden, we've got a picture of it and it is a rectangle, is, got it, to be constructed, okay, no math there, using a rock wall, still no math, as one side of the garden. Look at your picture and make sure that one side is marked stone wall. All right. So if you want, you can even write this down in words so that you draw your attention to the fact that that's a stone wall. And wire fencing, got it, for the other 3 sides. Okay. Well, I'm not very good at drawing, so I'm just going to do wire fencing around the 3 sides. Right. Given, okay, 200 feet of wire fencing. That needs to be written down somewhere. So 200 feet of fencing, wire fencing. Determine, which is just another word for find, the dimensions. Dimensions, well, that's length and width. Now in the picture, they've labeled them X and Y. So find the dimensions. So X equals y equals. That would create, got it, a garden, okay, of maximum area. So now we want to write down maximize area. What is the maximum area? Oh, they're asking us for something else then. So we need to mark that down as well. Right. So the second time I read it, I have all the information that's important to solving the problem written down either on the picture or next to the picture as part of the information that I've gleaned from the problem. Okay, so I'm looking to maximize area. So I want to highlight the area. So this is my objective function, if you will. This is what I'm trying to optimize. And I've got these other dimensions and these other variables. So the other variables that I have are X and Y. So I need to relate X and Y together in an equation. So I have also 200 feet of fencing. So I know a couple of things. I know the area of that region will be X times Y. And I also know that the wire fencing is a maximum of 200 feet. And that should be equal to 2X plus Y. Now, that is part of the constraint because based on the picture, I have two sides of length X and one side of length Y because the other side of length Y is a stone wall. So my perimeter goes around three sides, 2X plus Y, and that's got to be covered by the 200 feet of wire fencing. Now, somebody make a suggestion on what we could do in order to set up an objective function so that we could solve this problem. What's something that we could do next?
Solve 200 feet equals 2X plus Y for one of the variables.
Yes, so Lindsay suggests taking the 200 feet equal 2X plus Y and solving for one of the variables. Which variable is the easiest one to solve for?
Y.
Y is the easiest one to solve for, so that's going to be the one that we're going to go for first. So we're going to take our constraint equation, which is 200 feet equal to 2X plus Y. This is the constraint. This is the objective function. That's our objective to maximize the area. And we're going to solve for Y. So Y equals 200 feet minus 2X. And then we're going to take this and we're going to substitute into the objective function. All right. So the next thing that we're going to have written down is the area equals X times 200 feet minus 2X. And then we can multiply that out and get 200 feet X minus 2, oops, I've got my parentheses in the wrong place, minus 2X squared. All right. Now we need to maximize or maximize our area. So we're looking to maximize the area, optimizing it. And in order to do that, we need to find the relative extrema. So to find the relative extrema, we have to find the critical values. So the critical value that we're looking for is going to come from critical points. So let's find those critical points that are on the graph. First, we have to take the derivative. So we're going to take dA with respect to what variable? How do we know what to take the derivative with respect to?
To X?
Yes, got it to be to X because we don't have anything else left. So that's the point of reducing the objective function to being a function of only one independent variable. There's the dependent variable, which is the variable you're after to optimize. And then the independent variable is the only one left. So you take the derivative with respect to that one variable. So that's going to give us 200 feet minus 4x. Now, critical points come in two varieties. So when we look at critical points, we get either the first derivative is 0, or we get the first derivative does not exist, but it's in the domain of the function. In other words, the function does exist. Now, our first derivative exists for all values because it's polynomial. So we have none of type 2. And for type 1, we take 200 feet minus 4x, set it equal to 0. So 4x is 200 feet, or x equals 50 feet. So we only got one critical value. Now we have a choice. We can do the first derivative test, or we can do the second derivative test. And I'm going to demonstrate doing both on this problem, and then probably we'll use the second derivative test the most often because it is shorter. So using the first derivative test, I would make a number line like this, and I would have 50 in the middle. And then I would look for the sign of the first derivative at test points. So, test points here. I would probably use even something like 1, and then I would use 51. So if I use 1 and I plug it into the derivative, which is up here, 200 minus 4 is definitely positive, so that's not a problem. And then the next one, 51, would give me more than 200, so this would be negative. So this is increasing to decreasing, so I have relative maximum at 50. Now, I was looking to make the area as large as possible, so I do want a relative maximum. If I got a relative minimum, it would not actually solve my problem. My problem is to maximize area, and that might mean it's not possible to do. Now, what does the second derivative test look like? The second derivative test is actually more useful in optimization problems. For the second derivative test, we find the second derivative. So d squared of a by dx squared. We take the derivative again, we just get -4, which is always negative, which means it's concave down, so it's a relative max. So as you can see, it's shorter and there's less work to do. Now, it only worked because it gave me a non-zero number. If it had given me 0, then I would have had to go back and do the first method again. So I like the second derivative test for optimization problems. Now, that gives us just the value of x at the relative maximum. It does not give us the value of a. So if we're coming back up here, remember that I want the area at the maximum. So to find that value, I need to plug it back into this equation right here. So this is my original function that you see highlighted in blue, 200 feet x minus 2x squared. So let me create a little bit of space. Oops. All right, so that was my original function, area as a function of x. And now I'm going to plug in the 50 feet that I got up above. So I'm going to find the area when x equals 50 feet. And this gives me 200 feet times 50 feet minus 2 times 50 feet quantity squared. 200 times 50 would give me 3 zeros after a 10. So 10,000 square feet minus, let's see, 50 feet squared is 2,500 times 2. I'm getting 5,000. You guys check my arithmetic there. And so I'm getting 10,000 minus 5,000, which is 5,000, and this would be square feet. 5,000 square feet. So going back up to the beginning, I can fill in X is 50 feet, area is 5,000 square feet. How do I find the value of Y?
In the original formula, you just plug in the area in X and then divide the area by X and get Y.
So back to the original up here in my original constraint equation, remember I solved it for Y in terms of X. So this equation right here, Y equals 200 feet minus 2X will give me the Y value. So that gives me 200 feet minus 2 times 50 feet, which is 100 feet, which gives me 100 feet. All right. So again, make sure that you're putting blanks at the beginning of the problem so that you're sure that you've got all the information that was asked for in the problem when you're done. It didn't just ask for the area, it didn't just ask for X, it asked for all 3 dimensions. Now we want to look at number 2, and I have a piece of cardboard, as you might expect, to help explain what this does. So we'll read it first, and then we'll solve the problem. So in this particular one, starting at the beginning, we have, you are constructing a cardboard box with the dimensions of 2 meters by 4 meters, which is huge, by the way. Okay, that's not a cardboard box. It's got to be a steel box. You then cut equal size squares from each corner so you may fold the edges. What are the dimensions of the box with the largest volume? So there's a picture right here that shows the box, and it shows the corners that are going to be cut out. So you can see in each corner, the length of the corner is X and X. In other words, it's a square. So you're going to cut equal size squares from each of the 4 corners so that it will look like this. All right, this is going to be what you're going to end up with when you're done. All right, now once you're done, you're going to take this and you're going to fold up the edges. So you're going to fold up this edge, fold up that edge, fold up that edge, and fold up that edge. And then it will create a box, and you'll tape the edges together. So it creates a box like this. Does everybody kind of get a clue to what you're doing here? Now, the height of the box is one of these flaps that has been folded up. So the size of that flap coming up is going to be the height of the box. And the size of the flaps are X. So the height of the box will be X. All right, so here's what it looks like when you cut them out, and here's what it looks like when you fold them up. Okay, let's take a look now back at the words, and we're going to go through and translate. You are constructing a cardboard box with the dimensions 2 meters by 4 meters. All right, so when we're done, we're gonna have 2 meters by 4 meters. Now, actually, to tell you the truth, this is actually poorly written now that I'm thinking about it. It should be you are constructing a box from a rectangle with the dimensions of 2 meters by 4 meters. So let's add that in there because otherwise it's ambiguous. From a rectangle with the dimensions 2 meters by 4 meters. That makes more sense. All right, that's logical. Okay, now the next thing we want to do is, it says, so the first thing I should do is draw my picture and label the sides, which I drew. There's a picture here, 2 in width, 4 in length. You then cut equal size squares from each corner. Stop right there and go mark off X by X, X by X, and so on in each of the 4 corners of your larger box. So you may fold the edges. What are the dimensions of the box with the largest volume? So we're looking for the dimensions of the box. So I'll call it length of the box, width of the box, and I want to maximize volume. But it didn't actually ask me for the volume. It just asked for the length and the width to make it a maximum volume. But it didn't ask me for the maximum volume. So I don't need to find maximum volume. I just need to find the length and the width. Now, when I get over to here, I've got 4 here and 2 here, but I don't have the length and the width and the height on this box labeled. So let's label the different sides on this box. Now, first off, the first thing to notice is that when you fold it, this side right here becomes this side right here. And it's actually 4 minus 2x because I cut x out of each end of the length. So I'm missing 2x. And so the length of the box becomes 4 minus 2x. And then I can look at the width, which is 2 minus 2x. And that becomes this measure right here. Which is the width of the box. It started out 2 meters, and then I cut 2 squares from each corner, each of length x, and that gives me 2 minus 2x. Now the piece that I'm missing isn't in the picture on the left, but it is in the picture on the right. And the picture on the right, I need the height. But when I fold up the corners of the box, the height will be that length x. So the height of the box is going to be x. So let's label this side here as x. So this is my height. This is my width. And this is my length. So I have length, width, and height of the box, right? Now, in order to get the volume of the box, I need an equation that relates the length, the width, and the height of the box. So I'm going to have to relate length, width, and height. So I have volume equals length times width times height. And that's going to give me h, I'm going to put the h at the beginning, times 4 minus 2x. Well, I should, instead of writing h, I should write x. And 2 minus 2x. All right, everyone with me so far? Now, we have a bit of a problem here in that we need to multiply this out in terms of one particular variable. We do have only one variable, which is x, and we're trying to maximize the volume. So this is our objective. And we do have some constraints, but we haven't written them down. Our constraints are L is greater than 0, W is greater than 0, and X is greater than 0. L actually has, or X has some more constraints on it. If
Yeah.
I cut a side of X off of this short side right here, I can't cut too much or this side won't exist, right? So if I cut 1 meter from each corner, I've cut the whole thing off. So X has to be smaller than 1 meter. Does everybody see that? If you're looking at the shortest side, which is the width, and I cut an X distance from each side, I still want to have some left to fold up. So whatever that is that I cut off, since the whole side was 2 to start with, half of 2 is 1. So I've got to cut less than 1 from each corner to still have something that I can fold up. So I have a constraint on X, which is that X is less than 1 and greater than 0. Okay. Now we can go ahead and
But
multiply.
I
Yes,
have a question.
go for it.
X cannot be 2 either.
No,
I mean, yeah, that falls
right.
into, that has to be into, yeah, never mind.
Because of the other side. If you're over looking at the long side, the whole length is 4, so half of it's 2, so it's definitely less than 2. But I'm taking the more restrictive one, which is that it has to be less than 1. All right, it's also got to be less than 2, but if it's less than 1, it's automatically less than 2. Okay, so let's multiply this out. So I've got, well, let's see, negative 2x times negative 2x is 4x squared times x is 4x cubed. You guys check my algebra here. And then I've got a negative 4x in the middle and a negative 8x on the outside. So that's a negative 12x times x is a negative 12x squared. And then I've got 4 times 2, which is 8. And 8 times x will give me plus 8x. So this is the volume equation that I have. V is equal to 4x cubed minus 12x squared plus 8x. Now, the 4 carried units of meters and the 2 carried units of meters. So I should actually have meters squared on this one, and I should have meters on this one and on, nope, that's it. I don't have any on the first one. All right. Now, what are we going to do for our next step? We need to maximize the volume. So we need to find the critical values. To find the critical values, we find the first derivative. So dv dx is going to be 12x squared minus 24 meters x plus 8 meters squared. That's the first derivative. Now we have a choice. We can do the first derivative test or we can do the second derivative test. Does anybody have a preference? I'm not getting any preference. You should have a strong preference here, guys.
I feel like the second.
Probably the second. What is our problem going to be in this particular problem? If we're looking for critical values, it is polynomial. So we know that we will have no critical points of type 2, right? So we're looking at critical points. So we have type 1, f prime equal to 0, and we have type 2, f prime does not exist, but it's in the functions domain. All right. So we have none of type 2. And what are we going to have to do in order to find the critical points of type 1?
Factor out, but it's kind of hard
Yeah, it's
because
kind
we
of
will
hard.
get
So we can write it as 12x squared minus 24 meters x plus 8 meters squared equals 0. We can divide every term by 4, at least to start, to reduce the values a little bit. And that is enough to tell us right away what about what's left. Does it factor?
No.
Nope, it does not factor. It's going to be prime because when you have 3 and 2, you're going to get at least 6 if you multiply those together, plus the other one would give you 7. There's no way to just get 6 in the middle. You either get 5 or you get 7. So you're going to have to use the quadratic formula. So we have x equals the opposite of b, which is 6 meters, plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a, which becomes 6 meters over 6 plus or minus the square root of 36 square meters minus 12 times 2 would be 24 square meters, all divided by 6, which is going to give us 1 meter plus or minus the square root of 12 meters squared over 6. The square root of 12 is 4 times 3, and the square root of 4 is 2. So we get plus or minus 2 meters square roots of 3 over 6, which reduces again, and we end up with 1 meter plus or minus the square root of 3 meters over 3. All right, which is as simple as it can get. So we have 2 possible values here. We need to approximate the 2 possible values because they have to be what? What constraint do we have on x? X has to be what?
between 0 and 1.
Between 0 and 1. So we need to make sure that these values are between 0 and 1. So when we're looking at these values here, what do we end up with?
1 is greater than 1. And the other one, I don't know.
All right, so 1 meter plus the square root of 3 over 3 meters, and 1 meter minus the square root of 3 over 3 meters. This one turns out to be approximately 1.58 meters. Does that tell you something? What does that tell you right there?
It's outside of our
We don't
constraint.
have to use it.
It's outside of our constraint. We don't have to use it. Is it a critical point for this equation? Yes. Is it a critical point for this problem? No. This problem carries an additional constraint where x can't be greater than 1, so we can omit this one. If you did not omit it and you continued to follow it, you would find that it is a relative minimum. And because it is a relative minimum, it doesn't maximize the volume. So you would still get the right answer. It would just be more work. All right. So the next thing I'm going to do, instead of doing the test points, is I'm going to go ahead and find the second derivative. So I have my first derivative right here, and I'm going to find the second derivative. So copying back the first derivative. Now I'm going to find the second derivative so we can get some practice at the second derivative test. This is 24x minus 24 meters, and then 8 meters squared, the derivative is 0 since it's a constant. So then I want to plug in my value for the critical point, which is about 0.42 meters. And so when I plug this in, I get 24 times about 0.42 meters minus 24 meters, which is going to give me something that is what? Positive or negative? If you actually plug it in, you actually, the true value is -8 square roots of 3. It's definitely negative. What does that tell you? When the second derivative is negative, what do you know about the graph at that point?
Concave down.
It is concave down. When the graph is concave down, you have a critical point. What's the only kind of critical point you could have on a concave down picture?
Relative maximum.
Got to be a relative maximum. So this is concave down. So we have a relative max at x equal, I got to find the real value again, 1 meter minus square root of 3 over 3 meters. All right, so we have a relative maximum there. Now, at this point, I have lost the train of what it was I was doing. So I'm going back to the beginning to figure out what I was trying to find. I'm trying to find the length and the width. So coming back to the beginning, I've got to find the length and the width. So when I come up here, I've got a formula for x, but I don't know what my other values are. So I've got the length though as 4 minus 2x, and I now know x. And I've got the width as 2 minus 2x, and I now know x. So now I can find the length and the width. But again, I had to go back to the beginning because sometimes by the time you get down to the end of the critical point, you've lost the train of what you're trying to find. So L is 4 minus 2x, which is 4 minus 2 times 1 meter minus the square root of 3 over 3 meters. And if you work out all of the arithmetic and algebra here, you end up with 2 meters plus 2 square roots of 3 over 3 meters. Right? And the width is 2 minus 2x, which is 2 minus 2 times 1 meter minus the square root of 3 over 3 meters. So the 2 distributing on the 1 meter gives us 2 minus 2, so that cancels out. And then we get just the 2 square root of 3 over 3 meters, right? And that is all that we were looking to find. Now, if we wanted to find the volume, we could take that value, and the value of x, and we could multiply them together, and that would give us the volume. But we were not asked to find the volume, so we do not have to get the volume. Questions about that one?
Yeah, I have a question. So the second derivative test is just plugging in the value, the critical point we got from the first derivative test, and
Yes,
seeing the
second derivative. So
Yeah.
the second derivative test, you find the critical points from the first derivative. Then you find the second derivative, you plug the critical points into the second derivative. If you get a non-zero number, it worked. If it's positive, it's concave up, so it's a relative minimum. If it's negative, it's concave down, so it's a relative maximum. If it's 0, the test failed, and you have to go back and use the first derivative where it's increasing, where it's decreasing. Okay, that's the second derivative test. Okay, let's take a look now at our next example, which is a suitcase on an airplane. The first one I don't think is too bad, but in general, the suitcase problems are some of the more challenging ones that you're going to find. So we'll work through these pretty carefully. Right. So we'll work through these pretty carefully and make sure that we're following each step. So to carry a suitcase on an airplane, the length plus the width plus the height of the box must be less than or equal to 62 inches. Assuming the base of the suitcase is square, show that the volume is equal to the height times 31 minus half the height quantity squared. What height allows you to have the largest volume? So we have two things that we have to do here. We have to first prove that the volume is equivalent to this in terms of just the height. And then we want to maximize the volume and find the height that does that. So basically, we're trying to solve an optimization equation where we get everything in terms of the height. Now, here's a picture of a square base suitcase. You have no idea how long I had to hunt for this image. They are not that common, but they do exist. So it's a square base. And we're going to go back to the beginning and we're going to add up or translate the words 2 to 3 at a time into mathematics. To carry a suitcase on an airplane, nothing to write down yet, although we have a picture of a suitcase. The length plus the width plus the height of the box, we should write that down. Length plus width plus height must be less than or equal to 62 inches. Assuming, okay, the base of the suitcase, got it, is square. Assuming the base of the suitcase is square. Okay, well now I got to draw another picture. So here's my suitcase. And I am really not good at drawing these, but okay. Oh boy, that was really bad. Let's try that again. Okay, it's somewhat better. All right, so the base is a square. The base is a square. On this picture, I can't see the whole base, but on this one I can. If the base of the suitcase is a square, well, if the base of the suitcase is a square, then my length and my width are equal to each other. And the only thing that's different is the height. All right, so really, if I want to write everything, say, in terms of, I don't know, one or the other, L maybe. I have L plus H less than equal to 62 inches. All right, so I've got that. Show, all right, that the volume, got it, is this. Okay. What height allows you to have the largest volume? So I'm looking for the height and I want to maximize volume. Okay, and I've got to come up with an equation for the volume relating the L's and H's. And I want it only in terms of H. Well, I could use this equation right here to get something for L. So I'm going to use my constraint, which is right here, to get something for L. So I have instead that 2L has to be less than equal to 62 inches minus H, which means L has to be less than equal to 31 inches minus H over 2. Oh, that looks like it's going in the right direction because I see this expression right here in this equation up here. So that makes me feel more confident that I'm setting this up correctly. So now I can say that that is going to equal the length. And so I'm going to let that be my value for the length. It has to be less than or equal to that. So I'll let it be equal to that. So my volume is going to be L squared H, or HL squared. So I'm going to have H times 31 inches minus H over 2 quantity squared. Well, that's what they asked me to find for the first one. So I've done the first part. The second part is what height allows you to have the largest volume. Well, that means solve it as a critical value. So finding the critical points of the first derivative and then locating where the extrema are. Okay. So now what I'm looking for is I want to go ahead and, ew, kind of nasty, but I need to multiply that out because I have to find the critical points. So I'm going to multiply this out first since it's a lot of work to do. So 31 squared, I think it's 961. Somebody check. 961 square inches. And then if I multiply these together, I get negative 31 inches H over 2, and I double it. So negative 31 inches H, I think is what I get in the middle. All right. And then I multiply. Is that right?
Couldn't we do product rule if we find it
Oh,
easier?
I'm not doing, oh yeah. You could do the product rule. I didn't even think about doing that. Yeah, let's do that. That might be more fun. It wouldn't, well, yeah, it would be product rule. You could also do product rule. You do product rule, and I'm going to finish this way. We'll see which one is easier. I think it's going to be kind of a toss-up when you get to the end. I agree the derivative would be easy in this form because you could do product rule and chain rule. But I'm a little concerned that when you're done, you'll have two things to multiply out, but maybe not. So try it that way and we'll see what you get. And then negative H over 2 squared would be plus H squared over 4, I believe. All right, so I've got H squared over 4. So now what I want to do is distribute the H and write it in descending order. So I'm going to have H cubed over 4 minus 31 inches H squared plus 961 inches squared H. And that's my volume, right? And then I'm going to take the derivative. So dV dH, which is going to be 3 over 4 H squared minus 62 inches H plus 961 inches squared, right? Then I've got to find the critical points. That almost certainly without question does not factor. So I'm going to have to use the quadratic formula. I didn't say it would ever be pleasant doing an optimization problem, but now I'm going to find H by setting that equal to 0. So I'm looking for critical points. So my type 1s, set that equal to 0. And my type 2s, there are none because it's polynomial. And if it's polynomial, it exists everywhere. So there are none of that type. So I have H equals the opposite of 62, negative 62 inches is 62 inches plus or minus the square root, negative 62 inches squared minus 4 times A, which is 3/4, times B, or C rather, which is 961 inches squared. All divided by 2 times A, which is 3/4. Now, 62 inches squared. And this is going to give me 3/2 in the denominator. Is going to be 3,844 square inches minus the 4's cancel and I get 3 times 961, which is 2,883, and it's inches squared, all divided by 3/2. Now the 2 will flip up to the numerator. So we'll have 2 times 62 inches plus or minus 2 times the square root of whatever that comes out to be. What does it come out to be? 3844 minus 2883, 961 again. That's kind of weird. 961 inches squared, all over 3, which is 124 inches over 3, plus or minus 2/3. And I'm not 100% sure if that has a square root. Let's see. Oh, the square root of 961 is 31. I think I did know that. Times 31 inches. So coming down here, we get 124 plus or minus 62/3. So this is going to give us 186/3, and these are all inches. And if I subtract 62, this gives me 62/3 inches. Right? Lots of algebra. Okay. Now 186/3 reduces to 62 inches. And 62/3 is 20.6 repeating inches. Which actually that's exact. So I don't need the squiggly equals. Right? Using the bar makes it exact. Okay. Now we could do the first derivative test or we can do the second derivative test. Our first derivative is this right here. All right, so when we're looking at the first derivative, if we want to take the second derivative of the volume with respect to the height, we would get 2 coming to the front, and 2 times 3/4h minus 62 inches would give us 3/2h minus 62 inches. All right. So using the second derivative test, if I put in 62, this is going to be a relative maximum and relative minimum at these values. Or 62, I think, is a relative minimum, right? So at 62 inches gives me 3/2 of 62 inches minus 62 inches, which is positive. So it's concave up. So it's a relative minimum, which is not what I'm looking for. I'm trying to maximize volume, right? So I'm trying to maximize the volume. So that's my objective function. So I can ignore that solution, and then I can plug in the other solution into the second derivative, which was 20.6 or 62/3. So I have 3/2 times 62/3 inches minus 62 inches. The 3's cancel, this becomes 31, and 31 minus 62 is less than 0. So it's concave down, so it's a relative maximum. This is the one I'm looking for, right? So I'm looking for the one at 62/3. So the height that I was looking for is 62/3 inch. Again, this is one of the more difficult problems that we can do in the optimization section. I think, I don't know why, probably because of the inequality. It's just a little confusing. But again, just going step by step, you'll get to the solution. Now we do have one more suitcase problem. Coming to here. Okay. So this is similar to the last one, but a little bit different. So the setup is close, but not quite the same. So we need to read through it and make sure that we've got the right amount going on, or the right formulas set up. To carry a suitcase on an airplane, the length plus width plus height of the box must be less than or equal to 62 inches. Assuming the height is fixed, this is new, or constant, show that the maximum volume is given by the same expression as before. So we want to write the volume in terms of the height. Then, what is this fixed height that allows you to have the largest volume? Okay, this time our rectangle is not square. So we're going to go back to the beginning and we're going to draw a picture of our box. To carry a suitcase on an airplane, and this time I do have the sideways view so I can label all 3 sides. The length plus width plus height of the box must be less than or equal to 62 inches. That should be written down. Note also that length, width, and height have to be strictly greater than 0 or you have a degenerate box, right? A flat box, and that won't hold anything. Not that you can get a lot into a suitcase to carry on a plane, but still. Okay, assuming the height is fixed, is a constant. So let H be constant. What that means is H is not a variable at the moment. Right? So when we take the derivative, we'll have to be careful about whether we're allowing the height to change or we're not allowing the height to change. Assuming the height is fixed, show that the maximum volume is this. What height allows you to have the largest volume? Okay, so looking at the picture, I've got length on this side. I've got width on this side. And I've got height on that side right there. All right. Now, if I'm looking at this problem again, then I want to set up my equation. So largest volume means to maximize. Now, I know that my length and width and height have to add up to be less than 62 inches. And I know that individually, they have to be greater than 0. So my optimization equation is again going to be volume, which is going to be adding them all together. So now I'm going to come up with an expression for length again. So length is equal to 62 or less than equal to 62 inches minus W minus H. H is constant. All right. So again, this means that I've got a constant value here for H. It's not a variable, it's a constant. Okay, so when I'm doing this one, the next thing I want to do is I want to write the volume equation. So the volume equation is going to be length times width times height. And I'm going to replace the length with 62 inches minus W minus H, where H is a constant, times W times H. Now I want to get all of this written into one equation. So I'm going to move everything sort of together, all right? So the next thing I'm going to do is move the W and the H to the front, and then I will probably distribute it. So I've got a W times H times 62 inches minus W minus H. Multiplying that out, I get 62 inches WH minus W squared H minus WH squared. Now, here's the tricky part that's hard to keep in mind while you're doing this. H is fixed. H is a constant. It is not a variable, it's a constant. So when I look at this equation, I see three letters, V for volume, W for width, and H for height. But I really only have two variables. The dependent variable is volume, and the independent variable is W. H is an unknown fixed number, never changes. So if it's 31, it's always 31. It's never anything else. So I need to find the critical values. So I take the derivative with respect to W. So WRT stands for with respect to W. So my type ones, dV dW equal to 0, are going to give me 62 inches H minus 2WH minus H squared, set it equal to 0. That is my derivative. And my type 2s, I have none. All right. So again, I only took the derivative with W as the variable. So H was a constant, so it just multiplied along like the 62. So this gave me 62 inches H minus 2WH minus H squared equal to 0. Now I need to solve this for W. And when I solve this one for W, I get 2WH equals 62 inches H minus H squared. And then I can divide everything by 2H. And this gives me W equals 31 inches minus H over 2. All right. Now, it's still in terms of the unknown H, but H is a constant, even though I don't know what it is. Now, I can take the second derivative test. And I can find d squared V by dW squared, which again, I'm applying it to this expression right here, which is the first derivative. H is a constant, so that term drops out. Second term has a W in it, so I get a minus 2H. Third term does not have a W in it, so it cancels out and becomes 0. And I get that the second derivative is just a negative 2H. Now, h is a constant. It has to be greater than 0 and less than 62. So I know that this has to be a negative value, which means it's concave down, which means this is a relative maximum. Right? So once I know it's a relative maximum, I want to go back to my original problem and I want to find the volume. So I need to find the length, width, and height. So remember my volume. I'm going to need more space here. My volume is length times width times height. And I know my length coming from the original was less than equal to 62 inches minus W minus H, which means that it's got to be less than equal to 62 inches minus, and now I've got an expression for W, which is 31 inches minus H over 2 minus H. Is everybody following what I'm doing? I went back up to the original problem where I solved for L, 62 inches minus W minus H to find L based on W. And then I'm going to distribute the negative, which gives me 62 inches minus 31 inches plus H over 2 minus H, which is less than equal to 31 inches minus H over 2. So now I should have everything I need. My V is going to be 31 inches minus H over 2. My W was 31 inches minus H over 2 as well. So that's 2 of them. So it's squared times H. Now, going back to the original problem, that is what it asked me to find, that was the expression for the volume. And I did find it, but I found it assuming that H was a constant. This is probably the most difficult problem in the set. I think thinking about it, it's the more difficult problem. H was a constant, so I ended up with the volume in terms of width, and the height was a constant. I took the derivative with respect to W. Then I found the critical points, plugged the critical points into the second derivative, got that it was a relative max, came back to solve for the length, then multiplied the length and the width, which were equivalent together, and multiplied by the height and got this formula. Last question, what height allows you to have that largest volume? Now we're to take that equation and we're to find what that height is. So in order to find what that height is, we're now going to have to assume that that height is in fact a variable on the last part, and we're going to have to take the derivative and find the critical points. So we're going to come back here down to the bottom. And this time, let's do it the way that Juan suggested it. I haven't tried it that way before, but let's see how well it works. We can use the product rule, dv dh, which is going to be derivative of the first is 1 times the second plus derivative of the second factor, 2 times 31 inches minus H over 2 to the first power times the derivative of the inside, which would be times a negative 1/2. 31 inches is 0, but the derivative of negative H over 2 is negative 1/2. Okay. And
I have a
then
question.
the first one.
Sorry.
Hadn't quite finished. Okay.
I have a question.
Yep.
Isn't H supposed to be a constant?
It is in the first part. In the first part. Now we're finding.
So only in
that
the first
height.
part?
Yes, only in the first part. Now we're finding the height, so it's got to be a variable. It's confusing. Like I said, this is the most difficult problem. And now we've got to find the critical points. which this makes it a little bit harder. So what I did was I factored out one of the common factors of 31 inches minus h over 2 to the front, and that left a placeholder of 1 times the remaining 31 inches minus h over 2, plus the factor came out, so I had 2 times negative a half, which is negative 1 times h, so I got minus h. And then 31 inches minus h over 2 minus h becomes 31 inches minus 3h over 2. And this is the first derivative. Now to find the critical values, there are still none of type 2 because this would be polynomial. So my critical points are going to come from the zeros of the first derivative from type 1s. So dv dh equal to 0. So this is going to give me none of type 2. 31 inches minus h over 2 equals 0, or h equals 62 inches, I think, as one of them. And the other one would be 31 inches equal to 3h over 2. So that would be 62/3 inches. And then if I wanted to, I could do the derivative again, but to be honest with you, I don't want to take the derivative again in this point. So in this form, I'd have to do product rule. So instead, I'm going to do the first derivative test. Now, if you had done it the other way, the second derivative test would have been easier. So I know that coming down here, I've got a lower limit of the domain that they can't be less than 0. So you want to mark off the limitations on the domain whenever you're doing the first derivative test. If you have any vertical asymptotes, those divide up the domain as well. And so we've got 0 marked here, and then 62/3, and then 62. So 62/3, of course, is about 20.67. And then 62 is our maximum, right? We can't get larger than 62. And so when we're looking up here, I'm going to test 1 and 21. And I'm testing in the first derivative. So this is the sign of the first derivative. So when I'm looking at that, if I test 1, I get 1/2. So 31 minus a half, that's positive. And if that's 1, 31 minus 3/2 is still positive. So a positive times a positive is still positive. And so I know it's going to be positive on this part. And then when I'm looking at the next one, at 21, when I'm looking there, if I plug it into the first derivative, which I just scrolled away from it, so 21/2 would be 10.5. So this one would be positive. 21 times 3 would be 63/2, which is bigger than 31. So this would be negative. So I have a positive times a negative. So this one would be negative, which means it's increasing and then decreasing. So I have a relative maximum here, which is what I was looking for. Now, if you wanted to test at 62, you could, but remember that 62 above that is outside your range. So I think you're going to find at 63, they're both negative, in which case, if they're both negative, then you have a positive again. So you have decreasing to increasing. So this is a relative minimum. And we are not looking for a relative minimum. We're looking for a relative maximum. So we're looking for 62/3. Right? Which is the end of that problem. And again, the suitcase problems are by far the most difficult problems in this entire set. And I believe there is one suitcase problem in the homework set as well. So let's take a look at example 5. I like these kinds of examples. They're a little bit different, but I like to put things like this on tests. I do not like to put suitcase problems on tests. I like to put them on homework, but not on tests. So looking at this one, it's very simple. It says find the area of the largest rectangle that fits into the triangle with sides x equals 0, which is the y-axis, y equals 0, the x-axis, and x over 4 plus y over 6 equal 1, which must be a slanted line that comes down here. So coming back to the beginning, all I got out of this is I've got a graph. That's really all I got. I'm drawing something and I've got limitations. That's all I got. So coming back to the beginning, it says find the area. So I'm looking for area of the largest rectangle. Largest rectangle means maximize the area that fits, okay, into the triangle, got it, with sides, okay, the y-axis, x equals 0, the x-axis, y equals 0, and x over 4 plus y over 6 equal 1. Okay, so I'm trying to fit a rectangle into this shape right here. Now, there are all kinds of rectangles that could fit in here. So let's draw some example rectangles so you can kind of see what they look like. And I'm going to highlight them in yellow. I'll draw them kind of small. Let's see if the yellow shows up. If it doesn't, I'll use a different color. So one, no, that really doesn't show up. So that's not going to do well at all. So let's try this color. That's not too bad. There's a rectangle that fits under the triangle. You can see it has this length and this height. Notice that it is touching here at some value, xy, that is on that slanted line. And so the length of the rectangle becomes the x coordinate of that point, which is the x value on that line. And the height becomes the y value at that point, which is the y value on that slanted line. So I need to know more about that slanted line in order to know more about that particular equation. So when I'm looking at that one of the things that I might want to do is go ahead and take that slanted line and write it in a better, more useful form. So one of the things I might do is multiply both sides of the equation by 12. So if I multiply both sides of the equation by 12, then I can get rid of the common denominators. So, or the denominators 4 and 6. So this would give me 3x plus 2y equals 12. And then I can solve for y by moving the 3x to the other side. And then I can divide by 2. So this is negative 3/2 x plus 6. So that's the equation of the line and slope intercept form. And I've now written an expression for y in terms of x, which should let me find the height of it. So the width of this box, of course, is coming across here. And it looks like the width of the box is the x coordinate and the height of the box is the y coordinate. Now, it doesn't have to be located in that position. I could move the box so that the box is in a different position. That's really the best yellow, I guess. I could have the box like this. Does everybody see that? So that the point XY is up here. It's much narrower now. So the width is very narrow, but the height is much longer. I don't know which one's going to have the maximum area. That's what I'm trying to find. I want to find what box has the maximum area but still fits within that triangle. So now the next thing I'm going to do is write an equation that represents the area of that triangle, of that rectangle under the triangle. So the area is equal to the length times the height. And the length is given by the X value and the height is given by the Y value. So I have X times Y. I need to replace one of them. And I've noticed that each time I've done it, the coordinates of the point where it intersects the line give the height of that particular rectangle. So I know that I can replace the Y with the equation of the slanted line representing that Y value. So now I have X times -3/2 X plus 6, and this is my area. That gives me area only in terms of X. So I have A equals -3/2 X squared plus 6X. Now I want to maximize the area, so I'm looking for the critical values. So I need to find the critical points by taking the first derivative. So dA dx is going to be 2 times -3/2 X plus 6, which the 2's cancel, so I get -3X plus 6. Remember, there are two ways to get critical points. You can have a type 1, first derivative equal to 0. And type 2, first derivative does not exist, but the area function does. In other words, it's in the domain of the area function. And we didn't put any constraints on our X and our Y, but we definitely have them. Looking at the picture, I can tell that the maximum width for X is between 0 and 4. So I know that X has to be greater than 0 and less than 4. And I know that the Y value has to go between 0 and 6 because that's the maximum height of the triangle. So I do have constraints on both X and Y. Now that I've done my critical points and my derivative is polynomial, so I'll have no critical points of type 2. This is why we love polynomials. They're the best thing ever. And then we take the first derivative, set it equal to 0 and solve. So we get 3x equals 6 or x equals 2. Now we check to make sure that fits within our constraint, and it does. So it says x is 2, then we can find the y value by plugging it back into the equation of that line, which was -3/2 x plus 6. Which gives us a -3 plus 6, which gives us 3. This seems to say that the area, the
Wasn't it
maximum.
3/2
Go ahead.
X squared?
Did I mess up somewhere? Oh, I was just looking for y. I haven't done the area.
Oh, for Y?
Yeah, I was just looking for y. I haven't done the area yet. So my area would be x times y, which is 6. Well, we don't know that it's inches. What should we call it? Units. 6 squared units. All right. So our maximum area is 6 square units. And it turns out that the triangle or the rectangle that fits under the triangle that has maximum area, let me draw it in pink, maybe that'll show up a little better, is going to have width 2 and height 3. It's this one right here. So that particular rectangle has the most area of any rectangle that will fit and underneath the triangle. Okay. I love these kinds of problems. I think they're really good problems to have on an exam. There are some in the homework like this. There are some where it fits under a parabola. Same thing. The height of the particular rectangle is given by the y value on the parabola because that's where it intersects. All right, so that's how you set these up and how you consider.
Question. Could you go through it again? I got lost in why is the area gonna be will not be greater than 6?
The reason y can't be greater than 6 is because the maximum height of the triangle is 6. So if I made a box that was 0 wide, it could be 6 tall. But it can't be any more than 6. That's the maximum height and still fit within the triangle. And what's the maximum width? 4, because it's the maximum width of the triangle itself. Okay. Let me go over it again from the top. So we're looking for the maximum area. Area of a rectangle is going to be length times width, or length times height. In this case, the length is going to be the x coordinate and the height is going to be the y coordinate. So our area is going to be x times y. Now, when we look at a rectangle that fits underneath here, we notice that it has coordinates where it intersects that line of x and y. So the height of the rectangle is given by the y value on the rectangle, but also by the y value on the line. So we took the line and we wrote it in slope-intercept form, where we're solved for y, and then we used this to replace y in the expression of the area. And that gave us a function only in terms of x. So the slanted line is a constraint that the corner of the rectangle has to fit on that line. That's a constraint. The corner sits on that line. So it has to satisfy that line. Then we multiplied this out to get something that was second degree. And once we multiplied it out, we needed to find the critical points. So we took the derivative. We found the critical points, which was 2. Oh, one thing I didn't do, which I should have done. What did I forget to do? I forgot to test that it was a maximum. So I could do the second derivative test, where I do the second derivative of the area with respect to x squared, which would give me a -3, so it's concave down, which tells me it's a relative max. And I forgot to do that the first time. All right, rushing a little bit towards the end of class. So the first derivative set equal to 0 gave me the solution x equal 2. Then I can apply the second derivative test, which basically takes the derivative of the derivative, which gives me a -3, which is always negative, so it's concave down, which tells me I have a relative maximum at that point, at the point x equal 2. Then I want to find the y coordinate, so I go back to the slanted line, -3 halves x plus 6 to find the y value, and that tells me the y value there is 3. And then the area of it, of course, is length times width, which is 6 square units. And then I drew the picture. We have one more type to do, which is an open unbounded region. Now, it turns out that the open unbounded regions are not required to have absolute extrema, but they often do have absolute extrema. So even though they're not forced to, if it's an open region, it may still have an absolute extrema, which we want to look for, a maximum or a minimum. So now what we're doing is we're looking at a manufacturing company that makes right circular cylindrical cans to transport its food product. If the volume of the can must contain 354 cubic centimeters, what is the height and radius of the can that will minimize the surface area? Now, when you're talking about a can, I'm trying to find my cut apart. Aha, okay. You're talking about a cylinder. So the cylinder has 2 ends that are circles, right? So we have 2 ends that are a pi r squared. So in this particular case, we're looking to minimize surface area. This is one that we're trying to minimize. Most of the time we've been maximizing. So we need to come up with surface area. So we have a radius here, and we have a height, which goes to here. Now the surface area has two ends, so we have 2 pi r squared. This represents the top and the bottom of the can. All right. Now, what about the sides? If you take the sides of a cylinder, it's like taking a toilet paper tube. So when you look at the toilet paper tube, if you're looking at the end of it, it makes a circle with circumference 2 pi r. When you cut it open and unroll it, it makes a rectangle. So again, when it's rolled up, the circumference is 2 pi r, and that becomes the length, and the width is the height. So the surface area of the sides are 2 pi r h. Right? So that's the surface area of our particular can. Now it says we have this right cylindrical can. The volume must contain 354 cubic centimeters. 354 cubic centimeters. What is the volume? Well, volume is also equal to area of the base times the height. So I have 354 cubic centimeters equal to pi r squared h. This is a constraint. And this is my optimization equation, or my objective function. I'm trying to minimize the surface area. Okay. So this will let me solve for either h or r squared. And I'm probably going to solve this for h, since that would probably be simpler than solving for r, given that I'd have to take the square root. So instead, I'm going to solve it for h. And this gives me h equals 354 cubic centimeters over pi r squared. So now I can write the surface area formula again. 2 pi r squared, the top and the bottom, and then 2 pi r h, which is the sides, plus 2 pi r times 354 cubic centimeters over pi r squared. Now you have an r over r squared, so you can simplify that, and the pi's cancel. So I have surface area equal to 2 pi r squared plus 2 times 354 would be 708 cubic centimeters over r. And then we're looking for the height and radius of the can. So we're looking for r and h, where it's a minimum, where surface area is the minimum. So we've solved for the surface area in terms of r. I would probably write it in a slightly different form, so it's easier to take the derivative with r to the -1 power. Now, to remind ourselves what we're doing, we're looking for the height and the radius, and we want to minimize the surface area. So this is our objective, which is to minimize the surface area, but we're looking for the height and the radius in order to make that happen. So now that we have the surface area formula written all in terms of one variable r, we need to find the critical values. So there are 2 ways of finding critical values, and this time it's possible we might get a type 2. So our critical values come from derivatives of set equal to 0, so type 1, the derivative of the surface area, with respect to r equal to 0. And type 2, the derivative of the surface area with respect to r does not exist, but it's in the domain of the surface area. In other words, the surface area still exists. Now, the problem with this is when I take the derivative of this, the first thing I'm going to get from the first term is going to be 4 pi r. And then from the second term, because I have r to the -1, I get a -1 coming to the front, 708 centimeters cubed, r to the -2, which is the same as dropping it to the denominator and saying over r squared. So I have r to the -2, which of course is 4 pi r minus 708 centimeters cubed divided by r squared. So it looks like there's a type 2 because the second derivative does not exist if r is 0, but that's not in the domain of the surface area. If r is 0, we don't have a can. If the radius is 0, we don't have a can. And so we can ignore that one and go on to the next one. So what we're looking at then is there actually are none of type 2 again, since r equals 0 is not in the domain. Right? That's why that's not a type 2. So then we're going to take the first derivative and set it equal to 0. So we get 4 pi r minus 708 centimeters cubed over r squared equals 0. Now it's my personal preference to write it so that it's not with a negative exponent, but if you like the negative exponent, you're welcome to keep it. I just like my exponents to be positive when I'm solving. Now looking at this, I know that r cannot be 0 or it won't be in the domain. So the next thing I'm going to do is I'm going to move one of these to the other side of the equation. So I have 4 pi r equals 708 cubic centimeters divided by r squared. Then I'm going to multiply both sides of the equation by r squared to get that out of the denominator. I know that r cannot be 0, that's not in the domain. So there's no problem with having that equation and multiplying by r squared. So this gives me 4 pi r cubed equals 708 centimeters cubed. And then I want to divide by 4 pi. So this gives me r cubed equals 708 centimeters cubed divided by 4 pi, which gives me, well, what is 708 divided by 4? I'm not entirely sure. 177. So it is divisible by 4. I was a little surprised by that. So 177. So r cubed equals 177 over pi centimeters cubed. And then I'm going to take the cube root of both sides. And when I take the cube root of both sides, I get r equals the cube root of 177 over pi centimeters cubed. It's quite possible that 177 is prime. Certainly, I can't think of anything that multiplies together. No, it's divisible by 3 because it adds up to 15. So it's divisible by 3. Let's see if it has any. That gives me 59, which is not divisible. 59 is prime, I believe. So we're kind of stuck. So we're going to do 177 divided by pi. And then we're going to take the square cube root of it. So raise it to the 1 divided by 3 power. And that gives us about 3.834. And I'm rounding in that last decimal place. And that would be centimeters now, because I took the cube root of it. Right? Now, the next thing we want to know is this is the only critical value we got, but we're not guaranteed that it makes it a minimum, so we need to test it. So I'm going to test it in the second derivative. So here's my first derivative up here. So let's write the first derivative again and find the second derivative. So the derivative of surface area with respect to R was, scrolling back up, 4 pi R minus 708 centimeters cubed R to the negative 2. Let's check. I can't remember if that's what it was. Yeah, that's correct.
Yeah, that was it.
Okay, so now we want to take the second derivative to use the second derivative test, which with respect to R again would give me 4 pi minus 708 centimeters cubed times a negative 2 times R to the negative 3. So I can think of this as 4 pi. And then if I multiply negative 708 by negative 2, I get 1416, and it's positive. 1416 centimeters cubed over R cubed. Now the radius has to be strictly positive in order to have a can at all. It can't be 0 or a negative. So I know the denominator is always positive. 4 pi is always positive, and the numerator is positive. So it looks to me like this expression for the second derivative is positive no matter what the value of R is in our particular domain. So for R greater than 0, this is going to be positive, which means it's concave up, which means we have a relative minimum. Uh-oh. And let's see, I may have to close and shut down and reopen. Hang on.
So after this, after we find R, what I did is I plugged R in the H equation and found H, right?
Yes,
that
we
work?
need the height and we need the radius to make this happen.
Okay, and then I plug that into surface area, and that's all, right?
I don't think they asked us for surface area. I think they just asked us
Just-
for the radius and the height.
Oh, okay. Oh,
So we
I
do
finally got
have-
one problem done.
Yeah. So we do have a relative minimum, all right? So our value is the cube root of 177 over pi for R. And that was centimeters. And then for H, we can come back to this expression right here. And then we can find H. So this becomes 354 cubic centimeters over pi times the cube root of 177 over pi centimeters squared. So that's going to raise it to the 2/3 power, and I would probably just leave it in that form, but centimeters cubed over centimeters squared will give us centimeters. So we can be sure that we've set it up correctly. And then we could work out what this turned out to be. So this would be basically 1 divided by the quantity to the 2 divided by 3. Times 354 divided by pi again. I got about 7.67 centimeters, which is reasonable. All right. So we have a can that's about 3.8 centimeters in radius and 7.67 centimeters in height, which sounds reasonable. Okay.